Okay, good morning, everybody, and welcome to this plenary session. So we have the speaker is very well known, is Antonio Franchi, and today is going to speak about aerial robots for interaction and inspection, understanding redundancy for future capabilities. So just, to record, Antonio is a robotics and IEEE fellow whose research is dedicated to advancing the practical utility of aerial system for society. A central theme of his work is addressing the challenge of enabling aerial robots to safely and intelligently interact with their environment. He explores these topics as full professor at both the University of Twente in the Netherlands and Sapienza University of Rome in Italy. His academic path includes previous research appointments at the CNRS in France and the Max Planck Institute in Germany. His findings on decentralized control, multi-robot coordination, and aerial manipulation are detailed in over 200 peer-reviewed papers. This work, conducted alongside his student collaborators, have received recognitions, including a Best Paper Award at ICUAS 2024 and an IEEE RAS Award for Technical Committee Activities. Active in robotics community, he has served in editorial roles for IEEE Transactional Robotics and the International Journal of Robotic Research. To help connect researchers in his field, he co-founded the IEEE RAS Technical Committee on multiple robot systems through his involvement in European projects like how to assess aerial core and other arms. He and his teams develop aerial robotic partner designed to support human workers, aiming to make complex real-world tasks safer and more effective. So it's a great and a real honor for me, a great pleasure, to have here Antonio Franchi.
Thanks a lot for the introduction and for the invitation. It's a true honor to be here in front of you. By the way, to the people way on the back, you are going basically to miss half of the presentation if you are so far, because you won't be able to read part of it. So I really encourage you to come forward if you want. Even during the presentation, please come forward. First of all, I want to dedicate this keynote to all the people working with me in the joint lab I am co-leading between Twente University and Sapienza University of Rome. And it would not be possible for me to speak and to give this keynote without the help of all these people. These are just the people who have been with us in the last 3 years, more or less. There are many more even before, as you will see. So this is the storyline, I would say, of this plenary. I really took it literally. I read it's a keynote lecture. Okay, so it's not a clean keynote talk. So I try to have it as a kind of lecture as well. I will have four parts, and I call it a storyline because I hope it will be engaging and will be something to discover together. So first part, application and research pipeline. We started working on aerial physical interaction about 12 years ago, at least me. We worked on at the beginning on trying to have multirotors being stable while in contact with the environment when I was at the Max Planck Institute, and then applying different methods. We saw that full actuation was a very key element to enable physical interaction and also omnidirectionality. And then we went toward articulated and morphing platforms. We typically apply model-based control because we like to understand the why behind the problems and not just learning how to do things. And we also like to explore mechatronic designs because one of our motto is that software cannot fix physics. So there are things that can only be done through changing the design. Also, more or less at the same time, I also started to do interaction through cable to cables, also I call aerial cable manipulation. We worked on tethered multirotors, the modeling and control, and cable suspended systems. We did robust post-control physical interaction with the load considered as an end effector, communication-less control, and we are still very active in this field as well. So what is my research philosophy? I call it the innovation pipeline. Basically, the idea is to operate on parallel research tracks. I gave you two examples, physical interaction, cable manipulation, and also to operate at different technology readiness levels, all at the same time. So we have a level 1 in which we work on concept, math, simulations, and we do rigorous exploration of the field. We have level 2 in which we work on prototypes, proof of concepts. We basically try to answer the question, does the math survive the physics? And then we have level 3 in which we integrate systems. We try to have a higher TRL and robust integration, okay? And depending on the level, we can have collaborations with industry, collaboration with other academic partners, and of different type. And actually, this is a loop. It's a pipeline, but it's also a loop because new prototypes and integrated systems really steer new fundamental questions that can be used to feed the level 1. I give you now some examples of these levels. So this is, I would say, a level 3 highly integrated system that was developed by Xiao Sun, mainly as a main author, who was a postdoc at the University of Twente. And actually, the work where the theory behind this paper was published is at ICUAS 2023, or 2023, yes. So here yeah, as you wish. Yesterday there were the other lights. I don't know whether you can switch on the other lights. So here we integrated the full system. We take advantage of all the knowledge we accumulated together. See how spent time with the people who developed the previous algorithms and techniques, and made it possible to have this highly efficient and integrated system. Another level 3 type of work is the work we are doing in our auto-assess project, in which we try to have commercial platforms that are enabled in physical interaction, exploring the internal part, ballast tanks and cargo hulls of ships. The idea is to have drones that can work in dark, dirty, and confined spaces where it's very dangerous for human people. And this is everything without motion capture, using onboard SLAM and all the possible sensors you can imagine. And again, it's physical interaction. Level 2 type of research in the lab, we have that commercial drones are limited by under actuation, apart from very few exceptions. So we try to explore the limits of omnidirectional actuation, and also different type of sensors like optical tactile sensors. Level 1, this is again another example. We work, for example, on modeling the elasticity of the cable and actually the full dynamics of cables using PDEs. And we do a reduced order modeling to embed this in model predictive control. So far, it seems very promising. You can see, for example, a manipulation of a completely flexible cable and for doing pick and place, or manipulation and interaction with very soft objects. So the important thing is that even if it seems that we are very close to now touching the world, to something that works in reality, we should not, in my view, we should not forget that the full pipeline should be always filled. We should not be just happy and about the fact that we reached some result in high TRL and consider that all the questions, fundamental questions, then are solved. This is not true at all. So if we in our lab, or at least my lab, we want to focus on level 1 questions, basically I think we will fade into an integration service sooner or later. And then we lose our goal, our role as a long-term research entity. And so nobody will ever explore questions that cannot fit the near-term incentives. And also the diversity across maturity levels gives a lot of resilience. You are investing on things that may not be hype now, but might be turned very useful when the hype on current research or applications will go down. So diversity is very important. So this talk will be mainly about actually a level 1 question. So I will not show any video anymore about what we did, what we achieved at ITRL. Now we dive deep into more fundamental questions. And all what we have achieved in integration would not be possible without having answered the previous fundamental question. So this, by trying to answer to this one, what I'm going to do is to try to lay the foundations for future results in the next 5 or 10 years. The main question that I want to answer is, did we really understand redundancy in multirotor systems? We definitely know how to use redundant systems. We use allocators and control methods. We know how to design many platforms which are redundant with but I think we still lack a deeper structural view. So my working thesis for this keynote is that redundancy has become operationally useful, definitely, but the structure is still only partially understood. Okay, let's have a fresh look at redundancy. Redundant multirotors are multirotors in which the total branch can be generated in more than one way, and typically an infinite number of ways. So, and in order to do that, you need to have a number of rotors that is higher than the number, larger than the number of coordinates that can describe the branch task. So let me give you this table in order to distinguish between what is a redundancy and what is full actuation and under actuation. The two, redundancy and under actuation, are not connected concepts. You can have both or none of them. So, for example, you on the first column you see no redundant platforms. A quadrotor as a task space, the branch is 4-dimensional, and you have 4 rotors, or a fully actuated accelerotor on the bottom left as a 6-dimensional branch that can be executed, and it has 6 rotors. On the other side, any multirotor like the accelerotor with a 4-dimensional branch as with more than 4 rotors is redundant. So on the second column. And for example, the fully actuated octorotor on the bottom right is also a redundant system. So what I'm going to focus on in the talk of today, it will be this second column. Redundancy creates what are called fibers. What are fibers? Fibers are these lines, these curves that you see on the moving video, on the rotating video. They correspond to the points in the velocity space, and for velocity here I mean the rotating speed of the propellers, that give as output the same branch. This branch is shown for in this plot on the right. You see these dots. Each of these dots corresponds to a particular 2-dimensional branch. And then for each of those dots, you have one curve that corresponds to all the velocity that produce the same branch. Okay, so you can also think of it as the nonlinear null space of the task. In this case, this is the case with three rotors and a branch space of dimension 2. Okay. The allocation problem is to choose, when it's given as input a task, choose a point on this fiber. So for redundant multirotors, the problem is not whether you can or not do the task typically, but where to choose this point, how to choose it, how to actually implement this task. Typical answer to this question is to use energy. No, it's normal. You want to minimize the energy to choose the task that to choose the speed of the multirotor that minimize the energy. So you try to find the point on the fiber that has the minimum energy, and we commonly use this way of allocation. So we minimize the energy with the constraint of implementing the task. However, when we move along the fiber, there is another parameter, another quantity that changes, which is the responsiveness of the system. And this also depends on the task, on the operating point, sorry. The task can remain the same and the level of responsiveness can change. So here I use a parallel to make the concept a bit more trivialized, let's say. So a tennis player that is just that has to be still can be still, so have this task while just being relaxed and still, and in this way is minimizing energy, or can be in a position which is also still but prompt, ready to react, which is not minimizing energy, but is maximizing the responsiveness. This is something that is very well known in biology and in the biological systems. The biological systems, through what is called the co-contraction of agonistic and antagonistic muscles, they can decide whether to do the same task, so apply the same torque to the joints with a very low stiffness, very low promptness, or very low high relaxation, so reducing the amount of energy, or being very stiff, so also very prompt and very reactive to changes. So the question is, can redundant multirotors have the same type of behavior? So can we have some kind of paradigm that I call the flying muscles, in which multirotors can have a tunable promptness in the same way muscles have in biology? And the way to address this is going through math. Okay, so we need to define properly what is this concept of promptness. First of all, we need promptness only if we have bounds on the torque limits of the rotors. If we have an unlimited budget of torque for our rotors, we don't care about whether the system is in a prompt state or not, because it can apply infinite torque and reach any task very with a infinitesimal time. Okay, so only when we have limitations in the torques applied, which are related to v dot, to the derivative of the spinning speed, then we can talk about the need for having promptness. And what is a way to define these limitations? By defining a metric in the velocity, propeller velocity space. This metric is defined on the tangent spaces of the velocity space. So it involves v dot. It's a metric which measures the length of these v dot vectors and also the orthogonality between different v dot vectors on the tangent space. So if you see, we look at this diagram, we have here the tangent space on top left, the tangent space TV of the velocities of the propellers, where the accelerations live. This is the home of acceleration at a certain point for a certain velocity. What is a metric? A metric is a map from the tangent space to the cotangent space. But you have to think of it as basically something that measures how costly it is to accelerate. Okay, even if you don't know this terminology, it doesn't really matter. It measures the length of the acceleration and it tells you whether two accelerations are orthogonal or not. Then the nonlinear map that defines the task as a differential and which is connected to the space where the task speed, the task rate lives. What does it tells us, this space? It tells us how the fact that we are changing the task. We are changing it. And in order to understand whether it's easy to change or not in that point in the velocity space, we need to do an operation that in math is called pushing forward the metric. We take the metric from the space on the left and we push it forward to the right. And this is done through a composition of maps. In the end, from an operational point of view, you have this final matrix in coordinates, which represents the pushed forward metric. What do you do with this matrix operationally? You take the determinant and do the square root, and geometrically, this represents the density of the fibers. If we go back to the previous illustration in which we had the fibers representing the similar task, we might have points, regions in the space where those fibers are closer to each other. It means we are more ready and it's easier to change between tasks, or regions in the space in which the fibers are more spread apart. It means it's harder to reach the same task. The velocities, each propeller has to travel more space, change the velocity more in order to reach adjacent tasks. Here you see two surfaces, which are two allocators that have a low density on the top and high density on the bottom. Okay, so this is mathematically what readiness means for a nonlinear map that maps total space in a base space, the original space to the task space. So the multirotor map is a nonlinear map. So when you have velocities of the propellers here, VIs, and you map to the total force, generalized force, which lives in the task space. And it's a special nonlinear map, is a signed quadratic map. You have the sum, the linear combination of the signed square of the velocities of the propeller. So the idea is to apply the previous theory to this particular map. When we apply to it, we compute the density for this particular map, and we also compute the energy, and we try to compare these two objectives. Let's start with the latter, with the energy. J1 here, the green one, is the energy consumed at a certain configuration of rotor speeds. You have the linear combination of the cube of the absolute value of the speeds. This is just the power consumed roughly by each rotor while spinning at a certain speed in order to overcome the rotor drag. It is just the power, that's speed times torque. Okay. And the second term is a cost function that tells us how good we are implementing a promptness objective. So the promptness is something we want to maximize. In order to define a cost function, we take minus the density, which defines the promptness, squared in order to remove the square root. But any other definition could help. I mean, you could you take the logarithm or other definitions if you want to maybe implement a better optimizer, a more efficient one. So, but we have to decide the metric. So in this work, I decide arbitrarily the Euclidean metric, I here. But the open problem remains: what is the best metric to use? So when we use the Euclidean metric, the promptness cost as a particular form, which is this one. And then we can compute it for any generic multirotor that has n rotors. Let's now narrow down in order to have a grasping on the general n-dimensional idea, because it's sometimes hard to reason in n dimensions. And let's go to 2 dimensions. So we consider a cart with 2 propellers, and that can move only on along a line. So along this line, the only possibility is to exert a force, which is one-dimensional. Is this a redundant multirotor? Of course it is, because the number of ways this force can be implemented is infinite. And because you have 2 parameters, the speed of the 2 rotors, to generate just one scalar force. And this is given by this map here. Okay, which is just I'm just rewriting this map in the particular case. And we can write the 2 costs in this case. So J1 is this one, and J2 is this one. Let's look at the level sets of these costs, and you see that they basically represent kind of 2 norms, but one with a minus in front. What you want for one cost is for both costs is to go in the blue zone, the darker zone. So for energy, you would like to have a very small velocity speeds, but for promptness, you would like to have as high as possible. So in the global space, you can clearly see that for this case, but actually this is a general case, you have to increase the speeds a lot more to have more promptness. So they are really in conflict. However, this is a partial view, because you don't optimize. You remember the minimization. It's not a minimization in the whole space. It's the minimization with the constraint of to implement the task. What does it mean to implement the task? It means to stay on the fiber. So we need to look how these fields, these scalar fields, look like on the fiber when computed on the fiber. And a very interesting thing happened when we compute them on the fiber. So if the 2 propellers are producing force in the same direction, like this one or this one, and then there is a plus here in the constraint, and so the fibers look like elliptic arcs. You have a compact elliptic arc that is finite length and it stays there. When the 2 propellers instead they go in opposition, they generate a thrust that is opposed to each other, you have a minus here. And when you specify a specific task, you have a curve that is hyperbola. So they are completely different topologically because they are non-compact, and you can increase the norm to infinity by traveling along this fiber, keeping the task constant, keeping the task the one you want. So this is the cooperative, the top one is the cooperative arrangement of the propellers, or a working way, and the one on the bottom, or the magenta one, is the antagonistic way of operating. So the fiber topology decides whether you can tune the promptness or not. Let's see this more in detail. In the case the propellers are working on a cooperative fashion, both producing force in the same direction, and this is not uncommon at all. If you think of a standard multirotors, so you take these 2 propellers and you point them up, you have the same idea. Typically, you want the propellers to produce the force in the same direction to counteract gravity. You seldomly put forces opposite to each other. So actually, this is the standard case. But you see that the fibers are compact, and you cannot change much the promptness by moving on the fibers with this arrangement. So also the energy is not changed much. What we say that the Pareto front between these 2 costs is small, but you have a very low authority in tuning the promptness of the system. It's like if you have the tennis player, which has very small range of motions, you are not allowing the tennis player to actually be prompt to receive the tennis ball. Instead, when the fibers look like hyperbolas, and then you can actually increase the promptness a lot by staying on the same task, by producing the same branch. But this means in this way, you are increasing the promptness, keeping the task constant, but also increasing a lot the energy consumption. So the two costs, they really diverge a lot. So the Pareto front is very large. And this is the trade-off to pay if you want to have more tuning capabilities. And to convince you, to persuade you that this is not just something that is for the dual multirotor. Here there are simulations done together with Mirko Mizzoni on another paper that we are working on that shows how different allocators have a different level of energy and promptness. So you see when you do the allocation at low promptness, the promptness here is low, the energy is also low, because the maximum rotor speed is less than 200 hertz, but the derivative is quite high. So you need a high torque to change the speed of the propeller at this fast pace. You need a strong motor with high torque. When you instead go to a large promptness allocators, the derivative is very low. You don't need much torque to change the speed, but the power consumption is much higher because the propellers are spinning at much higher speed, so the drag is much higher. And in fact, you see that the promptness increases, but also the energy here increases. And this is an axarotor that is tracking a certain trajectory under a geometric controller. So in fact, you see six inputs. You don't only see two. The same map actually appears in what are called variable stiffness actuators. What are variable stiffness actuators? Are the robotic counterpart of muscles. In robotics, for many years, they have been studied, and now they are employed also in commercial quadrupeds, for example. They consist of two motors attached to tendons and to a single passive link. If you write down the map of the torque of this link as a function of the two tendon nominal lengths given by the motors, and then you compute it for a special fixed angle, for example, in this case it's 0, then you realize that the map that goes from x1 and x2 to the force resembles very much the map of the dual multirotor. You see the square here, a coefficient minus the same coefficient, the square of the other variable. Okay, so the fibers look exactly the same, and in fact, you can have basically an isomorphism between the two very different physical systems, but actually mathematically very equivalent. But they're very different physically because you are matching the length of the tendons with the velocity of propellers. This type of actuators are called variable stiffness because you can see that when you increase the promptness, in order to increase the promptness, you make the tendons more tense, you tighten the tendons. You also increase another scalar, which is the passive stiffness of the joint, seen from the outside. What is this? If somebody tries to operate on this joint, it will feel a different passive reaction without the controller doing anything. If the two tendons are more stretched or less stretched. So you can change by this mechanism the passive stiffness that the system will have. This is very good, for example, in leg locomotion to adapt in rough terrain, and depending on whether the terrain is rough or very well known or unknown, then you can have a lower stiffness in order for the system to be more adaptive, or when the environment is very well known or you want to have a more explosive motion, then you make the system more stiff. You can use it to store energy. It's very, very important concept. And the fact that is also clear is that this promptness and the stiffness, the active promptness and the passive stiffness, or even passive promptness, you can call it, are actually related. Even if they are different, they are monotonically related. So increasing one increases also the other. In fact, those actuators could have been called variable promptness actuators, in my view, as well. So in conclusion for this part, the flying muscle view of multirotors shows that you have an aerodynamic promptness, that is the density of the fibers, which defines a field. And then you have to compute in order to understand how the allocation works, these fibers, this field on the fibers. And they are strictly fiber dependent, depending on how you let the rotor operates in unidirectional mode, how you mount the rotors, which speeds you allow. In particular, you have this cooperative region in which the promptness and the energy are not much in conflict, a small Pareto front, but the promptness is very weakly tunable. And then you have these antagonistic regions in which the Pareto front is higher, and you can increase the promptness at the expense of the energy. So in this way, basically, I established this kind of isomorphism between multirotors and muscle actuated systems. The missing passive corner. So we can create a table in which in the first row we have variable stiffness actuators, and in the second row we have a dual rotor case. And on one column we have the active task responsiveness with the fiber density, the promptness, the readiness, as you want to call it. And we have seen that VSA has the active promptness, and also dual rotors have aerodynamic promptness, and they are very similar. But then we have seen that for the VSA, there is also a second column. There is the passive interaction, the passive promptness, the passive stiffness with respect to the environment. And we can define this passive stiffness, and in fact, this gives the name to the VSA. But on the lower right corner, we didn't see anything. There is no equivalent of this passive aerodynamic impedance or stiffness. So is it then the isomorphism basically broken by this, or can we find something to be put here that does the counterpart, or is the isomorphism really full? So think about it. Why we don't have this? Why we don't have the lower corner? The reason is in the variables that appear in the torque and in the force generated in the task generated by the two systems. In the torque generated by the variable stiffness actuator, it appears theta, the deflection angle. So we can take the partial derivative with respect to theta and compute this passive stiffness. In the force produced by the dual rotor, we have only the two rotors that contribute to the force. We cannot take any derivative with respect to any external environmental variable to define a certain passive impedance with respect to it. So we are missing this external variable. What could be this external variable? Could be the position of the cart, maybe. Maybe it's the thrust depending on the position of the cart. Can maybe then be the velocity of the cart? What do you think? Velocity of the cart? Can the velocity of the cart influence the thrust produced by the propellers? If the cart is moving, the propellers perceive a wind, okay? Like, but thrust maybe is influenced by wind. Yes, indeed, this is called axial inflow. And the axial inflow influences the thrust produced by one propeller. In particular, I don't have the time to go into a bit of a simple aerodynamics here, but basically, depending whether the inflow is in accordance with the thrust or in disagreement with the thrust, you have an increase of the thrust or a decrease of the thrust, of the nominal thrust produced by the propeller without axial inflow. And this increase or decrease is a multilinear in the velocity u of the air and in the velocity of the propeller. This is very important. So the velocity of the propeller still appears here. Otherwise, would be not good. Okay. We could not use the velocity of the propeller to tune it, to tune the relation. So you have a plus or a minus depending on these two cases. Here, for people more into blade element theory, you can see how the axial inflow changes the angle of attack. It can increase it or decrease it, and so it can change the, under a small angle approximation, you can linearize it, and you can see that there is this additional term. So when we look at these, look at this first. So when we include this effect in the nonlinear map, now the nonlinear map is not anymore the difference of the square of the velocities, but there is also this multilinear part, which depends on u, the velocity of the air. And this is an environmental variable. It's not anymore just something the controller can change. So if we put this force in the cart dynamics back here, then we can separate what we typically use to control the force of the two propellers and what is more belonging to an environmental effect, something that we typically neglect and we consider it as a disturbance in a controller, but which actually my take on it is that we can actually exploit it if we know it. And what is this term? This term is a damping term because it's a force which is proportional to a speed. And the coefficient, the damping coefficient, can be modulated by changing the speed of the propellers. So we have a tunable damper. And since we have two propellers, we can use both to shape the damping and also the force, the nominal force produced. Another way to see it is that we can actually define an equivalent velocity that will result by just applying constant forces. It's like the limit velocity that the cart will have. And the stiffness or the control gain, you could call it, the passive control gain, which that is done by nature at a certain speed of the propellers. And these two quantities can be tuned independently. And that is exactly the same thing that happens in the variable stiffness actuator. You can tune the resting angle, when the resting angle that is given by the two muscles, and you can tune the promptness. Okay, so what is the control effort if somebody tries to change the angle, or in the case of the aerodynamic case, if somebody tries to change externally the velocity to let it deviate from the equivalent velocity. And this control loop would be completely passive. And so the idea is that we can combine the passive and active controller by suitably playing this. And for n rotor multirotors, this will be for the rigid body in the Lie group, and there is room for extension. We still didn't develop the full math for it, but there is a lot of work to be done, in my view. That could be very interesting. We could enable basically a few things that I will recap at the end of this seminar. So the idea is that you basically in this way modulate the passive interaction of the multirotor with the environment, which is something that I've never heard of. Typically, we always actively want to control the multirotor on a certain trajectory, reject all the disturbances using closed loop, using whatever, even machine learning and anything. But the idea is always to track a certain trajectory or a force or behavior, okay? This is a different perspective, complementary, in which we tune the physical system in order to let the physics do the job. What is the advantage of doing the job? letting the physics do the job, is that we have infinite bandwidth. We don't need to go through computation. And here I try to just pose the two paradigms. Again, they are not in opposition. So classical aerorobotics paradigm, this is not only model-based, this is also deep learning-based, the black box approaches that are driven on the left, and the paradigm extension, which wants to include also the idea that we can tune the aerodynamics, the aerodynamic response of the system. If we try to study it more, and then, of course, we start with the math, but then we have to go in the lab and try to prove that the theory withstand physics, withstand the experiments. I now conclude my lecture with the last part, in which I will display to you some open questions and an outlook I have on this topic. So first of all, what we have seen, I think we have 3 takeaways we can take at least from. So the central concept is this geometric concept of fibers, and around it we have the concept of energy, concept of promptness, and concept of passive shaping. And the redundancy, which creates fiber, is basically this structural resource that we can use to organize the choices we can make in the matter of these three topics, let's say. Okay, if we want to tune energy, promptness, or the passive interaction of the system. If we understand well this structure before even trying to do anything, then our capabilities will become much larger, rather than just trying to do the job. What is the new viewpoint that this, let's say, theory tries to bring? Is that through geometry, you know which are the internal states that can do the task, the feasible one. Okay? So studying of the fibers is very important. We have a work that is currently under revision, in which we try to really describe the fibers of the full behavior of the fibers in the full n-dimensional space, but we could completely crack it only in the case of redundancy degree equal to 1, so 1 rotor more. In the case, for example, of redundancy higher than 1, it's still unsolved or partially solved. Then it's important to that the topology. So, for example, if there are parts of the spaces that are disconnected, or parts that are not accessible because of we have limits in the propeller speed, we have dead zones, and so on, decides really this topology, the tuning freedom that we have of the previous cost functions. And then we also, the new viewpoint is that we have this new isomorphism with a completely different domain in robotics. And we could read from this literature and get new ideas, because this field is much more developed. They've been working on it in the last 20 years. And we could try to bring from that field some new ideas and new techniques. Open questions. As Aristotle said before, we need to find the metric, okay? And this is not yet clear what is the best what is the best one. In the work before, I used the Euclidean one. There is also another work under preprint in which I define a different metric which takes into account the rotor drag and the torque limit. But yeah, this is really still open in my view. How the co-contraction and the Pareto structure extends exactly in a fully expressed way in higher dimensions is also open. And also how to exploit this passive promptness, which in my view, it has a lot of potential benefits, but it's not clear then how to put it in an actual control framework, and also how to measure it, how to measure what is its effect, and also whether we can prove this theory and really do the job of exhaustively tell for each canonical platform what can be done, what cannot be done, what is the typical passive promptness or the co-contraction, analyze this thing for typical canonical platform is not done at all. And also which new type of a control architecture can arise from this different view. There are many open questions. I could see if somebody is interested, there is plenty of open avenues to do research on. But why we should do research on it if we are interested in something that has an impact in the real world? Okay, there is a huge potential in my view. So we could have allocators that have a known structure. They can not just trying locally to overcome singularity and limits, but we could have a global allocator that is proven to be non-singular or proven to have a certain promptness, and so it's much better for stability and for certification, for example. We could trade off energy readiness and passive response much better. For example, we could do adaptive policies that raise the promptness only when it's needed, for example, to react a strong wind gust or just before an impact in physical interaction, and then go back to lower energy when it's not needed anymore. And they can also inform the design rules of completely new platforms. Thanks to the knowledge of this structure, we might completely redesign our multirotors in a way that is tailored for exploiting at best this concept. So we could have, in my view, by exploiting this, we might have aerial platforms that could fly possibly with a so much large span of wind speeds and turbulences, let's say, that we could have multirotors doing inspection in the North Sea 24 hours, 365 days per year, saving a lot of money. This is a big bottleneck of inspections, for example, in the North Sea, is the fact that they really have to wait, that they cannot do inspections if the wind is too high. They have to wait that weather says yes. But in this way, if we exploit this theory at its limit, I think we could say we can do the inspection whenever. And then you can also imagine the application for search and rescue and so on, because in cases of meteorological weather disasters, typically it's very hard to fly, also in case of fires. So I think it's gonna matter a lot. So also to conclude, I think it's very important that we don't immediately rush to have integrated systems in our community. It's important that we work on everything, and maybe there are some labs that work more on the integration, but still we need to keep a fire on the lower level, because there are many things that we didn't yet understand of multirotors and aerial systems. We should not be satisfied of what we achieved in terms of integration. This is not, I think, our role, at least my role as an academic. We have the luxury to have time and to be able to think ahead. We don't have to rush to deliver a product or to make our product and financial income, let's say, sustainable. Okay? We don't have to convince the investors and so on and so forth. So don't really get into this rush mode, but really try to understand better the structure of problems. So currently we have systems, aerial systems that work, and we can do a lot with it. We have models that can explain, but we have to use this in order to accumulate questions. Okay, this is very important to me. Not let the river of questions disappear. So we can progress much more strongly if the performance-oriented research and the structure-oriented research grow together. Thank you.